All right, so the that's the wrong day. Let me pull up today. There we go. Um, the plan for today is to pretty much finish up the chapter one PowerPoint. We might get all the way through it today. We might start the chapter two PowerPoint, or we might need to wrap up chapter one a little bit next time. These first couple of weeks are a little bit more flexible. Chapter one and chapter two, we can kind of cover a little bit more material or a little less. We can cover some additional examples or fewer examples. So the first couple of weeks are going to be a little more flexible as to what sections are covered at what pace. Note that I've also uploaded a YouTube playlist or created a YouTube playlist where I'll be uploading the videos. I decided to do that because I post the Zoom links, but you can really only watch those links at least easily on like a laptop or a phone or something. If you wanted to say like watch them on your TV or whatever, it can be kind of challenging to get that to work out. But with the YouTube playlist, it's a little more portable that way. It's a little easier to use. It's you can also, if you wanted to like subscribe to my channel or add the playlist to like your lists or whatever, you can have, it's a little easier to reference that way. Like all the videos are in one place instead of having to click different links. So I decided to do that. That link, let me show you where that is. So that link is in the useful websites tab. And I just added the link here. The YouTube playlist can be found here, and that here underlined is the hyperlink. So you can click on that, and that will take you over to my channel. And there is a stats playlist where we have the first couple of class meetings, and I'll be posting the class meetings as we go through the course. I might post them kind of in a batch, like once a week or something. I might not post them quite as quickly as the Zoom links because it does take more processing on my end to get them onto YouTube. But they will be up there in a pretty timely fashion. Yeah, somebody asked, are the study plans optional? Yes, the study plan on my math lab is optional. So you can do those if you want a little more practice, but it doesn't count towards your grade and you don't have to do that. And then note that there are a couple of sections of homework due this coming Sunday. So make sure that you don't miss those. So get onto my math lab or my stat lab. It's really called my lab stats, but I'll probably most of the time call it my math lab or my stat lab because that's what it was for like 10 years or 8 years or something before they rebranded the thing. So it's just like drilled into my brain that that's what I call it. And my lab stats just doesn't flow as nicely as like my math lab or my stat lab. So anyway, just note those homeworks that are due this coming Sunday. And then the quote of the day from question in chat. Yeah, it's perfectly okay to work ahead. And I mean, sometimes that can be advisable. If you feel confident with the material, feel comfortable with it, if you don't feel like you're burning through your attempts or something on material you don't understand, if you feel comfortable, definitely work ahead. If you're working ahead and you see that you're really struggling and it's getting frustrating, or you're using lots of your attempts before you understand a problem, maybe then I would say slow down and let the lectures catch up to you a little bit. That might be helpful. But if you're comfortable with the material, absolutely. And especially if you, again, like last time the quote of the day was about margin. If you say, not really that it would happen next week, but if several weeks from now, maybe you look ahead and you're like, oh man, next week I've got a big chemistry exam, I've got an English paper, a big paper due, and I've got the stats homework to do. Well, maybe you can knock out the stats homework a little bit ahead of time, put next week's homework into this week if this is an easier week, and then shuffle some things around so that maybe that makes your, say, next week easier so that you can handle that whatever chem midterm or whatever next week. So that's part of margin as well, is that time management idea of sometimes there are things you can shuffle around and things that can't be shuffled so easily. So yeah, absolutely, working ahead is not just allowed, but in some situations would be very advisable. And chapter 2, I'll probably post the chapter 2 homework, today or tomorrow or something like that. Yeah, definitely. You're welcome for the YouTube link. So I've started kind of posting more class material there over the last semester or so, just because I think it's a little easier for people to access than the Zoom links. Also, we have a whatever, I don't know what you call it, like an auto delete policy for Zoom. So they like automatically delete Zoom videos that are more than so old, more than 120 days old. So this way, these will be a little bit more permanent for you if, maybe not so much in this class, but in some of the classes like calculus or math 90 or something where they build on one another, that way people will be able to reference the previous semester's class material, where a lot of those Zoom links will, will either be dead links or the content will be deleted after a while. So it's also a little more permanent in that sense for you. But certainly if you were, going on and doing a second course in statistics or something and wanted to refer back, that might be a better way to do it. Okay. The quote of the day is by chess grandmaster Daniel Naroditsky. He has a YouTube channel, does streaming, does commentary. Fun guy to watch if you're into chess. Very informative for advanced beginner, early intermediate level. Which for me is a stretch. Like I'm certainly not at that at that level of chess. But so one of the things that I like, one of his philosophies is that there's a difference between an abstract advantage and a concrete advantage. So if anybody likes chess, an abstract advantage might be something like, oh, I'm ahead in development. Like I've got 3 of my pieces kind of out and active, and my opponent only has 1 piece out and active because they brought their queen out early and I got to chase their queen around a whole bunch. They moved their queen a bunch and I got all my knights and bishops out. So that's an abstract advantage because if I, go to sleep, if I, goof around for a couple moves, they catch right back up and I have no more advantage. Where a concrete advantage might be like, because I have my pieces out, I can start an attack and then win one of their pieces. And it's like, okay, that knight that I won, they don't get to have that knight the rest of the game. That's a concrete advantage. So in terms of things like academics, where does that maybe apply? Well, something like, coursework or obtaining a degree or something like that, in the sense of what most people's life goals are, that would be an abstract advantage. So getting a degree in the field kind of gives you something that will allow you to do something in the field that you want to do, to work in the career you want to work in. But having that degree isn't going to get you that job. It's not going to get you that career or that salary that you're looking for. Having a degree is an important piece of that. It's an abstract advantage, but you have to convert that to a concrete advantage. Same thing with different types of knowledge. For instance, knowing a whole bunch about physiology and nutrition and all of that versus actually going to the gym and exercising. This is something that I'm not so great at. There's a difference between knowing what exercises you should do to get fit or to get strong or whatever, versus actually having the willpower to go and do it. And I think this also ties in with that margin idea from last time, is if you have no margin, it's really hard to convert these abstract advantages to concrete advantages because they take time, they take a lot of high quality decision making and so on. Or another example is language learning, right? You could learn lots of stuff about a language. You can know that, oh, this language has this kind of a case system, or it has, these linguistic roots, so it's related to all these other languages. You could know a lot of things about a language. You could spend years learning about a language and about a culture and about a people, and still not be able to speak a sentence in that language, right? So those are just two different ideas. If I know a lot about a language, maybe that will help me learn the language more quickly or more thoroughly. But I actually have to put in the time to convert that abstract advantage to something concrete. And question in chat, in case I missed it, should we only work on the assignments portion in my stat lab? I wouldn't say that I would advise you to only work on the assignments portion, but the assignments portion is definitely the highest priority. So the assignments tab is where all of the graded material will be. So obviously the homework assignments will be there, but also when we have exams, the exams will be there as well. But I would say, yeah, exactly. Yeah. So that's the only stuff that's due. But if you wanted, additional information or content or practice, there's other resources like the study plan, like the ebook has actually quite a few videos associated with it that you can watch, just supplemental videos. So I wouldn't say, that's the only thing you should do, but that definitely should be the highest priority. That should be like priority 1, 2, and 3, is making sure to keep track of that assignments tab and to knock out those first. Yep. Okay, so let's jump into chapter 1, and let me redo my screen share here. So I'll swap some windows around really quick and be right back. Kind of resize everything to get everything looking decently in the window. Okay. All right. So last time we left off here talking about types of variables and types of measurements, types of data. And just to super quickly recap, we talked about variables being able to be split into 2 categories: qualitative with an L and quantitative, NT, quantitative. Qualitative like a quality, like a description; quantitative like an amount. We listed a bunch of qualitative variables, so things like shirt color or academic major. We listed a bunch of quantitative variables, things like number of books in a bookstore, height, age, things like that. We said that furthermore, quantitative can be broken into 2 subcategories: discrete quantitative versus continuous quantitative. And we said, okay, a lot of folks see these 2 words, discrete and continuous, and they think that there's a temporal element here, but that's not really the case. It's not a question of whether we plan to continue collecting data or not, or anything like that. Discrete versus continuous is about how we measure the data. So for instance, number of books in a bookstore, or well, let's go with something even a little clearer. We did mention that sometimes there can be gray areas, right? That there can be, this is an example of all models are wrong, some models are useful. There might be a gray area, but if we look even more clearly at, say, number of students in a classroom, if I look in this classroom and I see there's 8 students in there, if I got a really accurate measuring device, or if I looked really hard, or if I was really good at counting students, I would still get 8 students. I wouldn't say, oh, I brought in a more accurate measuring device, there's really 8.2 students in the classroom. We could say the same thing for number of books in a bookstore. We just might have to be a little more careful about how we define a book than we are in kind of regular language, right? If somebody accidentally ripped a book in half or something, does that count as like 1 book or 2 books or 0 books? We'd have to be just more careful about how we define what constitutes a book. But once we have that good definition, we'd be able to count the number of books in a bookstore. We wouldn't be able to say that there are there are 17.4 books in the bookstore because we had a more accurate measuring device. There's 17 books, 18 books, 16 books, something like that. So that would be discrete versus continuous. Something like, say, a person's height. A person could be 6 feet tall, but that's only approximate, right? If I had a more accurate measuring device, maybe I say they're 6 feet and 0.3 inches. If I got a little more accurate, maybe they're 6 feet and 0.31279 inches, right? With more accuracy and more care, I can add more decimal points of accuracy to my measurement. Okay, so we have this idea of qualitative versus quantitative and quantitative subcategories of discrete versus continuous. So let's look at the measurement scales. There are 4 measurement scales, and roughly speaking, the idea behind setting up these measurement scales is that the further down this list of scales we go, the more mathematical structure there is to the thing that we're evaluating. So the more mathematical operations there are that are legitimate to use on these types of measurements. So first we have nominal, then ordinal has a little more structure to it. Interval has even more structure, and ratio has the most structure of these scales. There are more things that we can reasonably do to say ratio data than to say ordinal data. Okay, so let's focus on this first measurement scale. So we have nominal data. Classifies data into mutually exclusive categories, which mutually exclusive means they don't overlap, in which no natural order or ranking is imposed on the data. Now, if you had to look at the variables, the variable types over here that we've already discussed, what would you say that nominal kind of lines up with pretty nicely? Placing into categories, there's no natural ordering or ranking. What does that sense?
Qualitative.
Exactly, yeah. So nominal is essentially nominal measurement scale is very closely related to qualitative variables. So qualitative variables are going to typically give us data that is nominal. Sometimes nominal is called categorical for categories, right? So like if we think of shirt color, for instance, we have, in a sense, we have some disjoint bins. We have red, we have blue, we have black, we have green. And, if I have a shirt that comes along, I'm going to toss it into exactly one of these bins based on its color. I can't have like a, red and blue bin or something like that. And again, all of these break down at some point. What if I had a shirt that was like a red body with blue sleeves or something? Like, well, you know, we can always find some kind of edge case where our model maybe is no longer very useful. But if we're thinking of, say, solid color shirts, then we can think of a model like this being useful. So exactly. So qualitative, really associated with nominal. There's really not very much structure here. In terms of mathematical structure, we can't add or subtract, the data. We can't say this one's a red shirt, this one's a blue shirt. What do I get if I add the two together? Right? Red plus blue doesn't make a whole lot of sense. We can't multiply or divide. We can't really even order them. We can't even say, okay, list the colors in kind of increasing order. That doesn't make a whole lot of sense. Now, again, you could really split hairs here and say, well, what if I'm a physicist? And what if, physicists tend to think of colors really being related to wavelengths? Well, maybe if a physicist was assessing something about color, say colors of lasers, they might think of that more as quantitative because that might relate to, say, the energy in the laser, and that might be what they're interested in. But we're kind of staying away from, any of that kind of discussion if we're just talking about general shirt colors, like preferences, for what a department store might want to order. If they want to, order more of the more popular shirt color type for their inventory, they don't really care what wavelength of light it's absorbing or reflecting. They just care how many people like red versus how many people like green. Okay, so the next three, ordinal, interval, and ratio, are going to have a little more structure. So ordinal builds in just a tiny bit more structure than nominal. And in ordinal, we can order the data. We can organized into categories that can be ranked. We can rank the data, we can order the data, hence ordinal. However, differences in the sense of subtraction aren't really meaningful. So when we say meaningful, what I mean is that if I go into the world, I make some observations, I collect a data set, maybe I end up with a data set that has maybe numbers in it, and maybe I could, take one number minus another number and kind of do that operation. But then the question is, when I do that, say subtraction of those numbers, does that actually tie to something meaningful in the real world thing that I'm trying to understand? Sometimes it does, and sometimes it doesn't. So this is as opposed to say interval, where we do have ranking or ordering of data, but we also have meaningful differences. So in interval, we can rank the data, we can order the data. We can say that when one data point has a greater value than another data point, then that thing in the real world has more of the thing we're measuring than the other. However, there's no meaningful zero. There's a couple ways to interpret meaningful zero, and that's really the defining characteristic of ratio data, is that there's an ordering or ranking, a natural ordering or ranking. Differences do exist. We can subtract data points in a meaningful way. And there does exist a true zero for ratio. So for ratio, a true zero, there's kind of two ways we can think about it. If I go out into the world, I collect my data, and I see that one of my data points has value 0, does that mean that for that entity that I measured, there's none of that quantity? If I see an observation of 0, does that mean there's none of the thing I'm measuring? That's a true zero. Another way we can think of ratio data is that division makes sense. In other words, if I have two things that I've measured in the real world, I get my data points, and one data value is twice the other. So my measurement is 2 versus 4. Does that mean in that real world sense, there's twice as much of the one thing as there is of the other thing? Now, you might look at this and say, like, is that ever not true? You might almost struggle to come up with examples of where that's not true. But I think we will see over here that there are some examples. So if we start with, let's say something like number of students in a class. If one class has, so let's go back one slide. If one class has, a measurement of 7 students in the class, and a different classroom has a measurement of 10 students in the class, 10 is bigger than 7. Does the second class have more students in it than the first class? Yes or no? Any thoughts? And I don't have my chat open just because I've got a bunch of other windows open. So if I have 2 classes, counting number of students in the class, one class I measure 7 students, the other class I measure 10 students, does the second class have more students than the first? Yeah, I think so, right? I mean, that's a pretty reasonable thing to say. If I have a class, again, 10 versus 7, the difference between those is 3. 10 minus 7 is 3. Is it true that that difference is meaningful? That kind of the second class has like 3 more students than the first? Yeah, I think that's meaningful as well. I think we have at least interval data. We have that amount of structure. Is there a meaningful 0? Again, 2 ways I could look at that. Is there a kind of a meaningful 0, or do ratios make sense? So if one class had, let's go with 5 students in it, and another one we measured 10 students, does the 10-student class have twice the number of students in it as the 5-student class? Well, yes, I would say so. Or another way to look at it, if I looked in a classroom and I counted 0 students, if my data value was 0, does that mean there are no students in that class? Well, yeah, I think that also makes sense. So here we have a lot of structure. We actually have ratio data. So for something like number of students in a classroom, there's a lot of mathematical operations that are valid to use on that data set. So let's look at something maybe like NFL rankings. So here we're just kind of saying, okay, I mean, I know this isn't exactly how the NFL works, but let's just say that we took every NFL team and they were ranked like first place, second place, third place, and on down, kind of like they do in each division, but just pretend we did it for the whole NFL. So NFL rankings like first place, second place, third place, or like, you know, race finishes in a marathon or something like that, you know, who came in first, who came in second, who came in third, you know, anything kind of like that. Okay, so if I consider two different places, somebody came in first place, somebody came in second place, they were one place apart, 2 minus 1 is 1. Is that really meaningful in the sense of, let's say, something like how long it took them to run the race, or how good they are, or something like that? That probably doesn't translate meaningfully. And this is why I would say that. So clearly we have a ranking here, right? I guess I didn't really say that, but clearly there's a ranking. So this is at least ordinal because we can definitely rank. So now we're checking whether differences are meaningful. And here's the problem. Well, let's go a couple further out. Let's say first place versus second place versus third place. Each of those places have a difference of 1, right? 1 to 2, 2 to 3, 3 to 4. These each have a difference of 1 place. So the data values are 1 unit apart. But first and second could have been neck and neck, and third place way back there, and fourth place kind of close to third place. Or first place could have, been Eliud Kipchoge and blown everybody out of the water, and second, third, and fourth were all like, fighting for second. Or we could have had, first was a decent bit ahead of second, who was a decent bit ahead of third, who was a decent bit ahead of fourth. So in terms of anything like the amount of time it takes to finish the race, or how good of a runner they are, or anything like that, that might be really what we're trying to get at here, it's unlikely the differences are meaningful, right? So having one difference between, your place versus somebody else's place, that could be a huge gap in ability, or it could have been neck and neck, or it could have been somewhere in between. So I would probably say something like NFL rankings, or places that you get in a race, who wins, who gets second place, or in a horse race or whatever. I would say that this is ordinal data. We don't really have that structure of subtraction really making sense. We can subtract, 2 minus 1, second place minus first place, and get a number 1, or third place minus first place and get a number 2, but that number isn't really meaningful. Now you might ask yourself, why are we going through this? Or why are we worrying so much about this? Why am I spending so much time on these points? Well, what we're going to see is, as we go through chapters 2 and 3, and we start trying to describe data sets, we're going to have lots of ways to describe data sets. Do you think it makes sense to describe, say, ordinal data in the same way that we might describe ratio data? Well, no, there are fewer things that are legitimate to do to ordinal data than there are for ratio. So the descriptive techniques that we're going to choose are going to be really based on what kind of data we have. Or even later on, the modeling techniques, the inferential techniques that we're going to use are going to really be driven by what kind of data we have here. And again, there are some gray areas, and there are some times where you debate, well, does this method really apply? Is it really the best method to use to make this inference, or to make this description, or maybe another one would be better? And there can, in some instances, be debate about that. So if we were to look at something a little further down here, like say temperature, So if we say, okay, 30 degrees Fahrenheit versus 40 degrees Fahrenheit, is 40 degrees Fahrenheit, 40 is bigger than 30. It's a bigger number than 30 is. Is 40 degrees Fahrenheit warmer than 30 degrees Fahrenheit? Is it like fundamentally a higher temperature? Yeah, sure. So we can order the data. There is a natural ordering. Do differences make sense? Does subtraction make sense? If I consider 30 to 40 to 50 degrees Fahrenheit, well, 30 to 40 is 10 degrees Fahrenheit different. 40 to 50 is also 10. Is the fundamental difference in temperature from 30 to 40 the same as that from 40 to 50? The answer there, you might need to know a little more, physics for this, but the answer there is yes. So going from 30 to 40 degrees Fahrenheit temperature is a certain increase in the amount of heat, in some sense, not exactly heat, but something like heat. And going from 40 to 50 is that same unit of increase in heat. So differences do make sense. If I say that there's a 10 degrees Fahrenheit difference, that implies the same thing, whether it's 30 to 40 or 40 to 50 or 72 to 82, it's the same meaning, right? Again, if I think back to my racers going first, second, third place, if I say they were one place apart, that could mean very different things between two places that were neck and neck versus two places where one blew the other out of the water. Is it ratio? Is it sensible to make a statement? So again, the question with ratio is true zero. Is it sensible to make a statement of the form, when the temperature measures 0 degrees Fahrenheit, there's no temperature, or there's like no heat? Well, no, right? I mean, it can go to negative 10 degrees and it's still like, there's still some heat floating around. It's just pretty cold. Or another way to look at it is, if it's 30 degrees outside one day, 30 degrees Fahrenheit one day, and 60 degrees Fahrenheit the next day, which, crazy Midwestern weather might do. If it's 30 degrees one day, 60 degrees the next day in Fahrenheit, well, one measurement is twice that of the other. 60 is twice 30. But is there like twice the amount of ambient heat or twice the temperature that second day than the first day? Well, no, that really doesn't make sense. So temperature, I would say, is not ratio, but it is interval. Can anybody think of a temperature scale that maybe does have a little bit more structure to it? Is there a temperature scale that we might argue is actually ratio? Any thoughts?
Kelvin?
Yeah. So somebody posted in here Kelvin. So exactly. So Kelvin doesn't get degrees. It's not degrees Kelvin. It's just this number Kelvin. So what is 0 Kelvin? Well, 0 Kelvin is absolute zero. I mean, maybe the quantum physicists would argue a little bit with this statement, but it's essentially 0 Kelvin is the absence of kinetic energy. It's the absence of something like heat. So 0 Kelvin, there is no heat. There's no wiggling around of molecules that is what we kind of call heat. So 0 Kelvin is absolute zero. It's zero thermal energy in the system. Again, there's a little bit of nuance there, but like for our purposes, we can definitely make that statement very confidently. Even the little like 0 point energy is going to be a tiny amount of energy that we might quibble about for that zero. But for anything we care about, that's a true zero. Or another way to look at it is to ask the question, like, is 200 Kelvin twice the amount of thermal energy as 100 Kelvin? And the answer to that is actually yes. Again, this might be a little deep into the physics or chemistry or science, but Kelvin is a ratio scale. So why do your physicists and chemists and in all these classes make you use this goofy Kelvin scale that's super annoying to use because it's just numbers that we're not used to dealing with? Well, that's why it has more structure than degrees Fahrenheit, and for that matter, more structure than degrees Celsius, which is also an interval scale. 0 degrees Celsius, I mean, what is 0 degrees Celsius? It's like where water freezes. It doesn't mean that like there's no heat or no temperature at 0 degrees Celsius, but 0 Kelvin does effectively mean that there is no heat energy in the system. Um, Kind of an interesting little side note about degrees Celsius. When they originally made the centigrade scale, the Celsius scale, it was 0 to 100, but 0 was boiling and 100 was freezing. And then a little later when they realized, oh wait, like temperature goes with energy, and the what we call energy, the higher energy is at the higher temperatures and so on. Then they kind of flipped it. But so interesting little tidbit there. There have been lots of temperature scales over the years, even temperature scales that really aren't interval, that are just pegged like different numerical values for for other temperature scales, not these three. We're just pegged to certain physical phenomena. We call, like, I don't know, freezing a brine solution, a saltwater solution, like 0 on the Joe scale, and we call freezing just pure water 10 on the Joe scale, and we call whatever, melting butter 20 on the Joe scale or something. And like that didn't really correspond to the same increase in energy from say this 10 units versus that 10 units. So there were even scales in the past that were only ordinal. Okay, so let's go through, and we'll go a little more quickly now that we've gone through a couple of them in quite a bit of detail. Let's go through and label each of these nominals over here, but ordinal, interval, or ratio. Number of books in a bookstore. Let's kind of get greedy. Let's just see if we can argue that it's ratio, and then if it breaks down, we'll back off. If we count the number of books in the bookstore, observe the number of books in the bookstore, and that observation is 0, does that mean there's no books in the bookstore? Yeah. If one bookstore has 1,000 books and another bookstore has 2,000 books, does the second bookstore have twice the number of books as the first one? Yeah. Ratios make sense. That's a ratio measurement. Number of Cheerios in a box. It's essentially the exact same process, right? If I look in my cereal box and there are no Cheerios and I'm sad because I can't have Cheerios this morning, if I count 0 Cheerios, there's no Cheerios. If one bowl has 100 Cheerios, another bowl has 50, the bowl with 100 has twice the number of Cheerios as the 50. Pass versus fail. Well, this isn't even really numerical, right? So I don't even really know what it means to observe a 0. And because it's not numerical, I really can't do division like I could with 100 Cheerios over 50 Cheerios and get a result of 2. I can't do like pass divided by fail. That doesn't make a whole lot of sense. I can't even really do subtraction, right? Pass minus fail doesn't make a whole lot of sense. But I can probably order them. I can say that passing is kind of fundamentally better than failing in terms of the goal of passing the course. So I would say that this is ordinal. Course grade as a percentage, that's probably going to be ratio. Right? If somebody like got nothing right in the course or did nothing in the course, their course grade would be 0%. And that's an R. That's just a very sloppy R. If one person earned 30%, another person earned 60%, the person with the 60 kind of earned twice as many course grade points as the one with 30. However, letter, if we just looked at the letter grade A, B, C, D, F, that's a little more, it's a little more along the lines of like place, like first, second, third place. there's definitely an ordering. A is a better grade than B is a better grade than C. There's a natural ordering there. But subtracting or dividing letters doesn't really even make sense from an arithmetic standpoint, let alone from a meaningful standpoint. I would say this is ordinal. Points per game in a football game, baseball game, something like that. If I observe a game with 0 points, does that mean that no points were scored? Exactly. That's exactly what it means. If one team got 20 points and the other team got 10 points, did the 20-point team get twice the number of points of the 10-point team? Yeah, exactly. That's a reasonable thing to say. That's going to be ratio. Ratios make sense. There's a true 0. Height or weight, similarly, going to be ratio. If one object weighs twice, or if the weight measurement is twice that of another, then there's like twice the amount of mass or twice the amount of weight between the two. Height, if I observe the height of a thing and it's like 0 feet tall, does that mean that there's no height? I mean, that would be kind of a goofy thing to try to do in a physical measurement, but that's essentially what we mean, right? So in physical measurements, observing a 0, does that mean there's none of it? It becomes a little more abstract, but I think the ratio question, do ratios make sense? Maybe is the better approach for something like both height and weight. So blood pressure, whatever, systolic blood pressure of 120 is that ratio data. So, and this might go, a little deeper into the science, but I would argue yes. So, it is a little bit difficult because there are things like, are we talking about pressure? Are we talking about pressure differentials? But I think within reason, we can say something like, when we put a blood pressure cuff on somebody and get a reading, when we get that reading, what are we reading off? We might call it like a pressure differential instead of a flat out pressure. But I think this would be ratio. There is like a true 0. If your blood's like not putting any extra pressure against the walls of your arteries, then you're going to read 0 pressure. Something like heart rate. So obviously there's an ordering here. Somebody with a heart rate of 100, their heart is beating faster than somebody with a rate of 90. Interval also makes sense. 90 to 100, 100 to 110, 110 to 120. Those are kind of the same unit of difference in the measurement, and it's the same kind of fundamental difference in the underlying thing we're measuring. And we also have ratio. Ratios make sense. Somebody whose heart is beating at 120 beats a minute, their heart is beating twice as fast, or they do twice as many beats per time period as somebody at 60 beats per minute. Age, whether discrete or continuous, whether we're talking about like number of full years lived or time since birth, again, I think that would be ratio. We certainly have an ordering. Differences make sense. Difference of 3 years, it's the same fundamental unit of difference whether you're going from 3 to 6 years old or 83 to 86 years old. It's the same elapsed time. Something like salary, also ratio. So we're seeing that a lot of the things that we measure, that we're interested in measuring, are ratio. But we do have to be careful because we do occasionally have things, pretty reasonable things, not crazy off the wall things, that could be different measurement scales. And then lastly, number of stars on an Amazon product. I guess last time we didn't get to this one, but this would be discrete. Like I can rank a product 0, 1, 2, 3, 4 stars. If we think of, say, ranking a certain product, or if we were thinking of like the average ranking, that might be continuous. But let's just think of maybe an individual's ranking. Do they rank at 1, 2, 3, 4, 5 stars? Here, I think we have to think a little more carefully. There is an ordering. if one person ranks it 5 stars and another ranked it 3 stars, the 5 is bigger than 3. And also the ranking of 5 stars means that they liked it more than the ranking of 3 stars. So we definitely have ordering. Do we have subtraction? Is subtraction meaningful? Is going from 2 to 3 stars versus 3 to 4 stars versus 4 to 5 stars necessarily the same amount of increase in liking the product or being willing to buy the product again or something like that we're interested in? Probably not, right? Something like star rating is probably a little more like first, second, third place than it is like temperature or something where there's a very consistent unit of difference between the different measurements. I would probably argue that we don't have enough structure here for this to be interval, that subtraction doesn't really make sense. So probably the best we can do is ordinal, saying that a higher star rating means that that product is preferred over the lower star rating. Could somebody maybe argue differently? Well, maybe they could. But my tendency here would be to go with ordinal. I don't think that going from 2 to 3 stars, a 1-star jump, 3 to 4, 4 to 5, those are all 1-star jumps. But I don't see enough evidence that those 1-star jumps are all similar increases in something more fundamental, like willingness to buy again, or like satisfaction with the product. And in fact, what you'll see is a lot of times there's like lots of 4 stars, lots of 5 stars, lots of 1 stars, and not a lot of 2 or 3. Like, if I just love the product, I'll rate it 5. If I like it pretty good, I'll rate it 4. And basically anything else, I'm going to rate it 1 star because I'm annoyed, right? Like, it's a little hard for us to tell the difference between like 1 and 2 stars. Like, am I slightly annoyed or am I quite annoyed at this product? We're usually just like, I just wasted my money, whether we're slightly or quite annoyed, and it's 1 star. And then even if we hypothetically, let's say that we thought that maybe the star system was interval, well, it really breaks down a ratio. Why is that? Well, I can't even rate it 0 stars, right? The rating system is 1, 2, 3, 4, 5. I can't rate 0 stars. It doesn't make sense to observe an observation of 0 stars. So really, if you're reading an Amazon review and you're looking at the star rating, it's actually a little more sensible in some manner of speaking. It's a little more sensible, instead of thinking of it from 1 to 5 stars, subtract 1 off of everything. So if you say this is 3 stars on a scale of 1 to 5, it makes a little more sense to think of it that as 2 stars on a scale from 0 to 4. That at least kind of slides everything over so that there's some semblance of ratio-ness to the data, although I would kind of argue that we probably don't have enough structure for it to even be interval. But if you counter argued against that, and you wanted to evaluate ratio, the ratio level, it definitely fails there, because a 0 measurement can't even happen in the star rating system. So it probably makes a little more sense to subtract 1 off of everything, think from 0 to 4 stars, and then the 3-star product would be like a 2-star from 0 to 4. And it's like, okay, maybe we think of that more as like halfway up the ladder, which is what a 3-star is. But then like a 4-star would be like 3/4 of the way up the ladder, right? And you can see how this biases maybe in favor of the higher numbers, because if we slid it further over to the right, if we said, well, I'm going to use 6 to 10 stars, 6, 7, 8, 9, 10, if we biased it more that way, our kind of quote 4 out of 5 stars will become a 9 out of 10 stars. And then it just like seems like a really good product at first glance. So by shifting the numbers to the right, I think our psychology, at least for most of us, kind of makes us inflate how good the product is. The more we shift it to the right, the more those kind of higher numbers are closer together, and maybe the less natural distance, in a sense, there is between them. So just kind of a side note on that. Now, again, like I said, I don't think that stars on Amazon or similar sites are even interval, so they definitely want to be ratio. But this is just for the purpose of kind of thinking about it and thinking through those star ratings. If you wanted to try to come up with something that was a little more like ratio, if you believed it was interval, maybe shifting to the left everything by 1 unit would help with that. Okay, so like I said in chapter 1 and in chapter 2 also, like there are some points that we'll spend quite a bit of time on and some that we'll kind of gloss over. So this next few slides is on collection and sampling, and we're not going to cover this in great detail, mainly because this doesn't have a lot of practical implication for the stuff that we'll cover in the course. That's not to say that this material is not important in a much broader sense. It definitely is. But for this course, where we're mainly focused on mathematics, it's an intro to probability and stats. It's not really an experimental design course. So we're going to gloss over this stuff, talk about it briefly, but we're not going to spend a lot of time on these next few slides. Oops. So there are some types of surveys for data collection that I've listed here. I've kind of split them into 2 groups. Telephone survey. So, Gallup polls might, randomly choose 1,000 people and call them on the phone and say like, hey, what do you think about such and such thing? They get answers and they combine those, they make nice charts and graphs and maybe make some predictions or inferences on that data. Mailed questionnaire, the most famous of these is the census. The US Census comes around every 10 years, and they mail one of these packets to every household. You fill it out, you mail it back in, and then that's how they collect the data. If you don't mail your questionnaire back in, they send a person to your house. So not like a police officer or anything, but just like a census worker kind of person. And they think, okay, maybe you forgot. They'd knock on your door and they'll just basically ask you the questions right there and fill it in. If you don't want to answer the questions, they'll answer as much as they can from just kind of looking around, like, do I see that there are kids in the house or not? Or, I mean, they're not going to like be intrusive or anything, but they'll just kind of ask, these questions. And if you don't want to answer, then they'll write down to the best of their ability the answers. So that would be like a personal interview. There also, when I was younger, they did this more. I don't see it as much in the malls these days. When I was a kid, though, I remember that like when we would walk through our local mall, there was this like business that operated in that mall, like a data collection business. And they would like approach kids in the mall and be like, hey, if you like give us like 10 minutes of your time, we'll give you like $5 or something, which to a kid was like, a ton of money. And they just have you like look at a screen and be like, oh, do you like for this product, do you like this picture more or that picture more? And, for their marketing or advertising or whatever. So they're just some kind of product research company. So it's another maybe like personal interview kind of thing. And down here, I also have 2 others, surveying records. So this might be something like looking at finance.yahoo.com to find historical stock prices, or maybe going down to, a government building to look up, whether it's marriage certificates or real estate, titles or things like that. Or observation. So just, the kind of sit on a street corner if you're a fashion designer, or if you're a buyer for a department store, sit on the street corner, and just as people walk by, if you're saying what's the hot color of shirt these days, mark down, this red shirt, green shirt, just observe people as they walk by and kind of keep a tally of what you see. And there are some pros and cons to each of these. These kind of top 3 are more active in the sense that you're putting more effort and time and resources into collecting the data. It's more costly, but you have more control over the data you collect. You can, call somebody up or mail a questionnaire that has exactly the question that you want to ask. If you're surveying a record, if I go to Yahoo Finance, I can get end of close values for the S&P or for a bunch of companies. So like end of day, close of the market. But if I wanted to, for whatever reason, wanted to know exactly at 2:37 p.m. every day, what was the value of that stock or that index, I'm probably not going to find that on Yahoo Finance, right? So if I want to know some kind of particular, slightly offbeat piece of information, surveying a record, I'm kind of at the mercy of what somebody else has chosen to collect and to record. Same with, like, say, an electronic medical record. Maybe, not everybody is assessed for this condition, or maybe not everybody has this test run on them, or maybe not everybody gets the blood work that's prescribed by their doctor. So I'm kind of at the mercy of what records have been collected, versus if I, were to do a more active study, I could say, like, okay, the participants in this study, we're going to have you all get blood work, and then we have everybody's blood work, for instance. Observation, again, more of a passive technique. These passive are going to be generally less resource intensive, take less time, effort. You might be able to get the answers more quickly. There's also a little bit less of a chance of personally biasing the results with passive versus active. But again, you're kind of stuck with the data that somebody else has chosen to collect, or that you can naturally observe. So talking about bias, in statistics, we use the word bias in a very specific way. There's also obviously the kind of colloquial way of using it. But we say that a statistic, which, remember, population versus sample. Population is the group of let's say, people, but the group that we want to say something about. So if I want to say, what's the average height of people in Pittsburgh? People in Pittsburgh, we've got a population, but it's almost never feasible to work with a whole population. So we work with samples almost exclusively. I take a sample of size 1,000 from the people in Pittsburgh. I compute the average height of that sample to get a statistic. So the statistic, the sample mean, the sample average. And then I hope that, and hope in a loose sense, will make this very precise later on, but I hope, or I calculate, that this sample statistic ought to be pretty close to the value of the population parameter, the population mean, that is really what I'm interested in knowing. So a statistic, a calculation based on a sample, we call it biased if it's calculated in a way that's systematically different from the population parameter. So for whatever reason, the way that I collected my sample and computed the sample average, if that was systematically different from the population average, there would be a problem there, right? And we would call that bias. And we have some sampling techniques to obtain unbiased samples, and by far the most important for our course is random sampling. Essentially what this means is you take everybody in the population, you assign each one of them a number, this person or this entity is number 1, 2, 3, and so on. You assign them a unique number. You randomly choose, if you want a sample of size 1,000, you randomly choose 1,000 numbers from that pool, and those 1,000 people that you've indicated are your sample. So that's random sampling. That's kind of like a lottery in a sense. There are some others as well. We're not really going to talk about them to a great extent. Stratified sampling, I will say one quick note on this, because it comes up in experimental versus observational studies. Here we have kind of multiple groups separated by a characteristic. So we might, let's say we're interested in investments. We might group folks into, say, younger folks versus older folks. Say, early career people, let's say 20 to 40, age 20 to 40, mid-career, say 40 to 60, or mid to late career, and then retirement, say 60 and above. And we might suspect that there's a difference in the investment choices between these three groups, or between these three strata. So I might look within each stratum, say the 20 to 40 group, do a simple random sample, and observe something about their investment selections, do that for the second stratum, the 40 to 60 people, and then for the third stratum, 60 and up, and then see if I can maybe see a difference in the, risk tolerance, say, between the three strata. And some others here as well. So again, not going to talk a ton about some of these slides. All right, so next topic, again, kind of on experimental design. we're not going to spend a lot of time on these slides either, but observational versus experimental studies. So an observational study, it's almost kind of self-explanatory. It's a study where the researcher observes what is happening or has happened. So there maybe is a variable that we want to get data regarding, maybe like productivity of our assembly line workers, how many, widgets per hour they produce. So we just, kind of go to the warehouse and say, okay, how many widgets came off of this line versus that line versus the other line, for each of the past 5 days or something. That might be an observational study. Typically these involve typically a little bit less bias. So if we, the researcher, in there kind of messing with the system and seeing what happens, we're kind of inserting ourselves into the system. We're risking an observer effect where with us messing with the system, it fundamentally changes the system that we're trying to observe, really for the purposes of knowing what's going to happen when we stop messing with it. So observational studies can help in that sense. One kind of caveat is that if if folks know that they're being observed and they care that they're being observed, then that's also going to change their behavior, right? If your boss installs all of a sudden a bunch of cameras all around you, like, you're probably going to be on your phone a little less, or, whatever, or maybe work a little slower because you're, paranoid now or something, or if your boss is like, all of a sudden you never see them on the floor, and all of a sudden they're on the floor every day this week, that's probably going to change people's behavior. So I'm not saying the observational studies are perfect, but they tend to be, a little more robust to those influences. An experimental study, the idea here is that we have a researcher that manipulates one variable, say an input variable. So this is the study or the process we're interested in. And then they measure another variable, let's say something like an output variable. Well, the input variable we call the independent variable, or sometimes the explanatory variable. This is the lever, in a sense, that the researcher is controlling. There could be, in a complicated study, multiple independent variables and multiple dependent variables. We'll just think in terms of one of each, but this idea generalizes to multiples of each. So the independent variable, the explanatory variable, this is the variable that the researcher, that the experimenter is manipulating, is controlling. And then what they want to measure over here is the dependent variable, or sometimes called the response variable. This is what we're measuring. So we change the inputs and we measure the effect on the outputs. Classic example of this is something like a clinical trial, right? We have a drug that we think works. We say, okay, I'm going to give some people 10 milligrams of the drug, some people 20, some people 30 milligrams of the drug. And then I want to see like how well the different groups do. Like, does the 10 milligrams actually treat the disease? Does the 20 treat the disease the same, better, worse? Does the 30 treat the disease same, better, worse than the other two? So they're the researchers manipulating the dosage, 10, 20, 30 milligrams. That's the independent variable, the explanatory variable. And they're measuring something like treatment effect, maybe like time to recovery from an illness, or whether the person recovers or not, whether the treatment's effective in some way. They're measuring that for each of the each of the values of the independent variable that they're changing, and seeing if they can kind of relate the two, right? They're saying, if I wiggle this lever over here, how much does this measurement over here change? Or does it change at all? Unfortunately, in experimental studies, these are often quite complex, like, doing where our black box here is basically the human body, quite complex. There are these insidious confounding variables. These are variables that the experimenter is not actively manipulating, and often that the experimenter doesn't even really know exist. They're kind of in the background, but they're affecting the dependent variable. They're affecting the measurement that we're making. So I wiggle this lever over here, and I expect it to be kind of like a one-to-one, in a sense, relationship to the change in the measurement of the output. But I see that sometimes when I wiggle this, the measurement changes a lot, and sometimes it changes a little for the same wiggling of the input for, say, different people. Well, maybe there's a confounding variable, right? Great example of this is in pharmacogenetics. Some people CYP3 enzyme is just a little wonky and doesn't work as well, and that means that certain drugs, say like some anti-clotting drugs, don't work great on those people, or really kind of don't work at all. So somebody gets a cardiac stent put in, they get this drug to keep them from to keep the blood from clotting around the stent, because it's just something kind of new that the body's not used to, and all of a sudden they clot the stent, and it's, they have heart problems a week later. Well, maybe it's that their liver just doesn't process this drug the same way that everybody else, or that most other folks do. So that might be like a confounding variable, right? I'm sure the original experimenters didn't really know about that, didn't think about that. And then over time, it's been realized, oh, wait, this CYP enzyme, if it's a little wonky in a person, that has this problem, right? We give them the anti-clotting drug that by all accounts seems like it should work. It should keep them from thrombosing their stent, but this confounding variable, this goofy CYP enzyme comes into play and changes the outcome in a way that we didn't expect from the input. So that's an example of a confounding variable. Maybe another example, a very popular example, is the placebo effect. And so particularly in studies related to anything kind of to do with psychology, but also more broadly than that, if we're, say, investigating a drug to treat, let's say, depression, and we say, okay, we're going to put these folks in our clinical trial, and we're going to give them this drug with this active ingredient that we think is going to help their depression. And lo and behold, we give them the drug, we measure their response to depression and say whether they get better or how much better they get, or something along those lines. And hey, everybody seems to be doing pretty well, or most folks seem to be doing pretty well. I think my drug works. Well, this placebo effect it's kind of the idea that, like, just by being treated for something, you kind of think that you're getting better. And that could mean that you falsely think you're getting better and you're actually not, but you just feel like you're getting better because you're being treated and you expect that to happen. Or this could mean, saying something like depression, you might actually get better as a result of being in the experiment. You might feel like, oh, I'm finally kind of like taking the bull by the horns, like I'm doing something about this. This is really positive. And then when the experiment ends, the effect maybe goes away. So maybe it's actually just being part of the experiment, being part of the clinical trial, that is producing the change in the measurement in the dependent variable, not the actual active ingredient of the drug. So how do we handle this? How do we try to get a handle on whether we think there are confounding variables, and maybe how much an effect we think that they're having on the dependent variable? And the answer is, typically we set up a control group alongside an experimental group. I would take my 1,000 test subjects, and I would allocate, let's just, for instance, say half of them to control and half of them to experimental. All of these folks are going to go through the experiment. They're going to go through the same process, have the same doctor visits, have the same blood work taken. They're going to be allocated in such a way that we make sure that we don't get like a whole bunch of women on one side and men on the other side, or a whole bunch of young people on one side and older people on the other side. We want to make sure that our allocation is random, but also is reasonably representative, and so on. And then what we're going to do is we're going to, again, put all of these folks through the same process with one exception. The experimental group in the example of, say, this pharmaceutical treatment gets the active ingredient. They get 10 milligrams of the drug in some pill. And the control group goes through exactly all the same processes, but they get no active ingredient. They even get a pill with the same coating, with the same inactive ingredients, but there's just no active ingredient put into this pill. So as far as the control group versus experimental group is concerned, the person going through the trial doesn't know whether they're in the control or the experimental group. They don't know whether they got the active ingredient or not. They're all being treated exactly the same, except for whether they get the pharmaceutical chemical or not in their pill. And then we measure the dependent variable, the response variable for each of these groups separately. So we've created two strata. We assess each stratum independently. And if we see that the experimental group gets better, there's seemingly a treatment effect, but the control group also gets better at like about the same rate, well, that would suggest that our pharmaceutical intervention isn't really the thing that's causing that effect. Maybe it's the experiment itself, because the control group had none of the pharmaceutical, yet they got better at the same rate. On the other hand, if we see the control group get better a little bit and the experimental group get better a whole lot, I say, okay, there's probably some amount of confounding with the experiment and all of that. That's why the control group got better a little bit. But the experimental group got better a whole lot more than the control group, whether that means a much faster time to recovery or much higher percentage of success or whatever that means. But if the experimental group does a whole lot better than the control group, well, then probably most of the effect that we're measuring comes from the change in the independent variable, comes from the pharmaceutical intervention, and maybe a small amount of the effect comes from the placebo effect or something to do with the trial. Okay. Sampling error is, so kind of shifting gears here a little bit. Sampling error, remember the population versus sample idea. We are almost always in the situation where we want to make a statement about a population, but that's too costly or infeasible to do. We're stuck making a statement about a sample and hoping that it generalizes to the population. But of course, if we're working with a sample, the sample is not the same as the population. We could have error as a result of that. I could happen to have a sample where I happen to have a little too many shorter people and a little too few taller people, and my sample mean height is a little lower than maybe it is in the population. Or vice versa. I could have a different sample with a few fewer shorter people than would be typical, and some extra tall people in there. And then my average height for my sample is going to be a little higher than it is for the population. So when I take the sample, even if it's a well-designed study, a good random sample, there's always going to be a chance that I get some extra shorter people or some extra taller people, and that throws off that sample average. And that's what we call sampling error. The fact that we're working with the sample instead of the population, we have to account for that. And that's essentially what all of chapter 7 and 8 is going to be geared toward, is how do we account for that sampling error. Statistical significance is another idea that will come up a lot in chapter 8. And we would say that a result is statistically significant if it's unlikely to have occurred by chance. In other words, if we don't think that it's the sampling error that's leading to something that seems a bit strange, then we think that it's something more fundamental. Okay. Again, more information on that later on in the course, particularly in chapters 7 and 8, but just to introduce some of these terms. In chapter 10, we'll talk about correlation and regression. And so again, just a very quick introduction to some of these terms, but we'll see a lot more detail on this near the end of the course in chapter 10. There's this idea of correlation, the idea that two different variables can be related to one another. So maybe like a person's height and weight, we might think would be correlated. We might think that if I know something about an individual's height, I can maybe make an inference about their weight. And maybe I know that if somebody happens to be taller than typical, I would expect they weigh more than typical, and vice versa. So that's a correlation, but super important, correlation does not imply causation. It doesn't necessarily mean that being taller causes you to be heavy, or that being heavier causes you to be taller. Sometimes we can make a logical inference, but oftentimes if we try to make too strong an inference on which direction the causation goes, or whether the causal relationship is even a direct one between these two variables, often if we try to make too strong a statement about the causality, we end up in dangerous territory. We end up making statements that just frankly aren't true. So one example is like, people say, oh, well, ice cream sales cause murders, because when ice cream sales tend to go up, murders also tend to go up, and vice versa. It's like, well, ice cream sales tend to go up in the summer. In the summer, people tend to be out and about doing more things. And for whatever reason, people seem to be wired in such a way that when we're around people more often, we tend to, experience more murders, unfortunately. So that's, kind of a spurious causation to say that, well, because the two are related, kind of empirically, I think one causes the other. It's probably just the warmer weather that's kind of leading to both of those. So again, correlation does not imply causation. Observational studies typically aren't good at teasing out causation. Experimental studies are better at identifying causation, still not perfect. Okay, and the last few slides are on misuses of statistics. And one important caveat to these few slides is, when I say misuses, this could be a statement of malevolence. It could be saying somebody is purposefully misusing statistics in order to try to mislead others. But I think quite often, if not a majority of the time, it's simply a mistake. Maybe somebody is honestly trying to present the data accurately and in an informative way, and they just made a mistake. They just, applied a descriptive technique to, say, a measurement scale that it really ought not be applied to, something like that. So saying that there's a misuse of statistics doesn't directly imply a statement about one's character or one's intention. And conversely, that also means that if we trust somebody, if we think that they're a good person and they wouldn't lie to us, we shouldn't necessarily trust their statistics. Even if we're quite confident they wouldn't be malevolent, or even if misusing the statistics in this way would be, detrimental to them, where we're like, okay, they have no reason to be malevolent. The conflict of interest is in the other direction of what they're arguing. We still ought to check their statistics, because they still might have just made a mistake. So the first slide here, I've kind of grouped this loosely into 3 slides. The first one deals with samples and sampling methods and so on. And a few examples of statistical problems that can come from samples are, well, one is sample size. We said we typically want to make a statement about a population, but we're stuck making a statement about a sample. Well, if my sample size is too small, the whole purpose of a sample is that it should look like the population, but just smaller. It should be like a microcosm of the population. My sample should be representative of the population. If I take a sample of size 2 from all people in Pittsburgh, if I get, if I'm measuring heights and I get like a young girl and an 80-year-old guy, do you think that's really representative of the cross-section of Pittsburgh? Well, of course not. Any sample of size 2 or 5 or even 10 for that matter is not going to be very representative. So too small a sample size, or in the extreme, say kind of a case study in the medical literature, these have to be taken in context. I have to be careful that I don't look at a very small sample, anecdotal evidence, 1 or 2 examples, and try to draw too grand a conclusion from that. very small sample, it's informative. It says, hey, this thing can happen. If you read a case study in the medical literature, it's like, oh, this interesting thing can happen. It's happened to somebody. It's a possibility. But I don't want to go turn around in my practice and then think that that's the situation that every one of my patients that has these symptoms is in. I can't generalize that from just this anecdotal evidence, this one person in this case study. If there was a huge study done with thousands of participants and we showed that 90% of folks that present with this constellation of symptoms have this disease, maybe that would affect practice. Maybe then I would say, oh, I see somebody with this constellation of symptoms. I think they probably have this disease. With a case study of one person, that's not nearly as convincing. So faulty, and maybe convincing is even the wrong word there, but that's not nearly as generalizable. Convincing kind of implies they're trying to convince me, but it's not nearly as generalizable. Faulty survey methods or data collection methods. Questions can be written, again, intentionally or unintentionally, in a way that's biasing. And even seemingly inconsequential things can actually bias answers. So one example is when a pollster is asking, let's say, about politicians, are you going to vote for politician A, B, or C in the upcoming election? If I always list this politician first, this other one second, and this other one third, that actually leads to a little bit of bias in the results. For some reason, the order that we read them can influence us. Now, if I'm like a really strong advocate for this or that politician, it's probably not going to bias me. But for the folks in the middle, or the folks who are just kind of picking randomly or whatever, I don't know, maybe they have more of a tendency to vote for the early person or the one in the middle or something like that. So good pollsters will actually randomize those results when they ask the questions. So sometimes this candidate will be first and sometimes another candidate will be first. And input errors, just recognizing the fact that going from the real world to a data set, this is a process that involves some interpretation and some data entry. And we could just, make a mistake recording the data or recording the measurement from the real world or entering it into an Excel spreadsheet or, and something like that. So just things to keep in mind related to samples. Bias I want to actually come back to because we could go longer or shorter on this slide. And we'll talk really quickly about the last slide here. So misuse is related to kind of statistics themselves, like how we present the statistical information. So one example that we'll see in chapter 3 is that, for instance, with measures of center, with something like an average, there are actually a lot of things like an average we can report. We can report the average, or what we call the mean, or the median, or the mode, or the mid-range, or the, root of these things that are qualitatively similar to an average. Which one should we choose to report? If I have a data set of size 20 and I report all like 20 different types of averages to you, this is supposed to be a descriptive measure. It's supposed to go from 20 down to like a couple of numbers that I can understand. And if I have as many averages that I report to you as original data, I didn't really get anywhere, right? So I have to pick one or maybe pick two. Which ones should I pick? Is there a good reason or rationale to pick this one over that one? Sometimes there is, but maybe not. So why did somebody choose the one that they chose? Inconsistent units, we'll come back to that in a minute. One that's kind of a little tongue-in-cheek, like statistics that aren't actually statistics, you see these all the time. Like something may have some effect. Well, what does that mean? Anything may do anything. A statement that's meaningful is something like, in a double-blinded randomized control trial, folks who took this medication had a 30% reduction in the risk of heart attack and stroke over a 5-year period. That actually says something, right? That's something that a person can set up their own study and try to confirm or refute it, right? A scientific statement has to be repeatable and refutable, empirically refutable. there has to be enough information, enough meat to that claim that somebody could set up a study. They could gather empirical evidence. They could kind of repeat the study that was supposedly done. They can gather more empirical evidence, and they can see if that evidence is in line with the statement or not. Something this amorphous, you really can't refute it with data because anything may do anything. What exactly do they mean here? And several other examples just with poor wording, or most of these were things that I've seen you know from at least fairly reputable agencies put out over the years. Misleading graphs we'll talk a good bit about in chapter 2, so that'll be in the next PowerPoint. Relevance, we could have something that is very statistically significant but that's not practically relevant. So I could say, oh, the p-value is like 10 to the minus 10. Wow, that's very statistically significant. And that, you understand exactly what that means in chapter 8. But you say, well, the effect size is like 1%. It's maybe we're very confident that medication A is better than medication B, but it's only so slightly better that we don't even care. So that's where relevance comes into play. I think we'll talk about inconsistent units today, wrap up, and then probably discuss bias next time and move on to chapter 2. We might start bias today, we'll see. So inconsistent units, this is something that we have to be fairly careful with, and this is something that we will see throughout the course. So my kind of very basic example for inconsistent units is, let's say we're collecting worldwide temperature data. So we build a little web crawler to crawl around to different weather sites in different countries and grab temperature data off of these sites. And we kind of average them together in some way and get what we think is kind of some kind of average global temperature. And then we report that, or we make an inference based on that or something like that. But the problem is, what if we have some countries whose data is in degrees Fahrenheit and other countries whose data is in degrees Celsius? I collect this information from the US and maybe, I don't know, 2 other countries in the world or something, and this data from other countries. If I just kind of lump all of these numbers together in a single data set, add up all the numbers, I mean, they're numbers, they'll add together. Excel will be happy to add them for you. And then like divide by the total number of numbers there are. Excel will do that too. I get something that I'm calling an average. But the problem is that I really can't add numbers with different units. I mean, I can, like if I just plug the numbers in, Excel will add them, but I ought not do that. What does it mean to add 30 degrees Fahrenheit and 20 degrees Celsius? That doesn't make sense. So these are inconsistent units, and I have to say move all of my data to the same unit. I need to do a conversion so that everything's in the same units. And then I can do my manipulations, my subtractions or averages or ratios or anything like that I might want to do. So you might say, okay, well, I mean, that's kind of obvious. Like, who's going to make that mistake? Well, I have an interesting kind of example here. So here's a chart of the S&P 500, essentially like the value of the stock market as a whole, from roughly 1928 to current day, so over about 100 years. And we look back here and we see on the left over here, these gray bars are recessions or depressions. This long gray bar over here, we look at this and we say, oh, that's supposedly the Great Depression, but it doesn't look all that concerning. I mean, the market, it was so low there anyway. Who really cares? I mean, our tech bubble and crash, our housing market bubble and crash, those look a lot worse than the Great Depression, don't they? I mean, what were all these people complaining about back in the 30s? Well, we have an issue of inconsistent units here. The S&P 500 is, these numbers are kind of roughly speaking dollars. So what does a dollar buy you in 2023 versus what did a dollar buy you in 1928? I mean, it's still like nominally the same unit. It's still United States dollars, but it's really not the same unit, is it? In 1928, a dollar bill probably bought you, I don't know, 15 loaves of bread. In 2023, you get 3 slices of bread or something. 2024, I guess, is our current year, huh? Still adjusting to that. So, I mean, nominally, maybe it's the same unit, but really fundamentally, these are different units. There's a sense in which kind of as every minute passes or every second passes, the unit of US dollar actually changes. And it's never really a consistent unit with itself. But we can typically say, if we're looking at a time span of, say, a few months to a year, maybe a few years, the US dollar is essentially a consistent unit over those scales. But if we're looking over 5 years, 10 years, certainly 100 years, it's very much not a consistent unit. One way that we can adjust for that, and we'll look at this in a little more detail in chapters 2 and 3, one way we can adjust for that is to do something along the lines of like either a logarithmic scale or looking at rates of return. And here's an example with just a logarithmic scale. Again, a little more discussion of this later on in other chapters. But on this log scale, we see a very different story. So when I kind of control for or take away the effect of that inconsistent unit of the US dollar over time, if I do that using a log scale, all of a sudden that Great Depression looks a lot greater, right? We look at the tech bubble and crash, and that's a minor blip. The housing market crash is substantial, it's substantive. But the Great Depression, like, holy, like, look at that on the left side over there. Now all of a sudden we really see that why it's called the Great Depression. So inconsistent units can be quite obvious, something like this, or it can be kind of hidden and insidious, and we're like, well, we're working with US dollars all the time, why can't I just take all of these S&P 500 prices over the last 100 years and just kind of average them? Because there's really a hidden inconsistent units here. So in finance, I would say that, say less than 5 years, they're probably consistent units, at least kind of roughly, at least close enough for most things that most people do, the accuracy that most folks need for most things that we're interested in knowing in finance. Probably if you're looking at a time frame of less than 5 years, it's probably close enough. Bigger than 5 years, I'd probably call them inconsistent units, US dollars to US dollars. And we'd have to do something to correct for that inconsistency. We might look at, say, annual rates of return instead. We might do something like put it on a log scale. We might, there are a couple of approaches we can take to try to handle some of that inconsistency. We might do something like inflation adjusted units. So there are a few different approaches. And again, I have a few different approaches, just like the measure of the center. Which one do I choose? Perfectly reasonable, sensible, knowledgeable, well-meaning folks can, maybe one person chooses one way of doing it, one person chooses another of handling this inconsistent unit. You have to make a choice. And choosing not to address the inconsistent unit is also a choice. You have to make a choice. Which one do you choose, right? It's not necessarily manipulative to choose one or the other. And I think one of the important takeaways from this course is to realize that these choices need to be made, and they need to be made maybe more often than some folks realize. So we always have to think about what choices are being made, what's the kind of psychological bias or of the person making the choice, what are the conflicts of interest, how does that play into the strength of their argument and our interpretation of the numbers they present. So again, next time we will talk about bias. we'll go through this fairly quickly. I'll pick out a couple of different types of bias to kind of talk about and to dig into. And if you want to next time, maybe look into some of these types of bias, just Google them or look them up in the textbook and see if there's one that you find interesting or that you find that really applies to your field. And next time we'll kind of, pick a couple of them and talk about them. Okay, so I do see a couple of questions in the chat, so I'll address those really quickly and then we'll be done. Sorry, when I have my kind of full screen up like this, I don't have the chat up because otherwise I think it makes it so I can't see things, and I think it makes it so it's harder for you to see things. Yeah, somebody says like the purchasing power of a dollar from 1928 would be about $1,800 today. I'm not 100% sure whether or not that's true, but it's certainly many times different. The kind of typical recent years, say in the last 50 or 60 years, estimate is that the purchasing power gets cut in half every roughly 20 years. Inflation's about 3.5% compounded continuously. And if you do the math, it turns out to be about 20 years halves the buying power, but that is compounded. So 40 years, it's a quarter of the buying power. 60 years, it's an eighth of the buying power. But also some of the stuff that happened around the wartime and around the Great Depression was really crazy, wonky stuff. So that, that rule of thumb doesn't really apply that far back. So that could definitely be the that could definitely be it could definitely be more times inflated than would be guessed from that rule of thumb. Would leaving the gold standard been considered changing the unit of a dollar? I wouldn't say that leaving the gold standard fundamentally changed the unit, because really what we're talking about is buying power of this currency. So my definition of a dollar or a fiat currency in general is it's evidence of past productive utility provided to the market that entitles one to an equivalent productive utility from the market in the future. It's essentially a store of value. And there are some other things that we could say as well. Leaving the gold standard allowed the dollar to float. It allowed that store of value to be tied to something different, something a bit more abstract. But so something like the productive utility of the country as a whole. But I wouldn't necessarily argue that directly changed the unit of the dollar. Now, did that allow the unit of the dollar to change more freely or less freely? I think folks on different sides of the debate would probably make different arguments there. I have a feeling that there's probably not a good consensus there. But yeah, I mean, that would be a great question to ask an economics professor. They might have a little more insight into that. But I think it's probably a bit more nuanced, because really what fiat currency is evidence of utility that allows you to extract utility later on. When will we use Excel? So really quick answer for the last minute. So Excel comes about more starting in chapter 2. It's not explicitly graded, but it will be very helpful for some homework problems, not for all the homework problems. I'll talk a little more about it in chapter 2. And again, the book introduces you to Excel, and there's also that Coursera course. Again, it's free to audit. That Coursera course, if you want something a little more structured, you can use that. Or of course, you can always just, if you come up on something and you want to do it in Excel, you can just Google how to do blank in Excel. So it's not explicitly graded, but yeah, it will be very helpful for, starting in chapter maybe 3, there will typically be a question or two near the end of an assignment that will be a little more data intensive, and those should be pretty clear that you'll want to use Excel on some of those. So the ones with 50 data points, you probably don't want to do by hand.